All right, so in this video, we're going to give some background on resonance. Um, resonance is something that's never going to go away. Resonance is something you're going to see again and again and again for the rest of organic chemistry. It's going to be a really big, important role for stabilizing structures from acid base all the way out to stuff that you'll see in Orgo 2. Resonance is really just a big fancy way of saying moving electrons. There are going to be a variety of different types of electrons that exist. There are electrons that are localized. Localized means you're stuck at a location. And then there are going to be electrons that are delocalized or able to be moved out to different spots. And resonance is really going to focus on our delocalized electrons. One of kind of the simplest examples of resonance is with a kind of like deprotonated carboxylic acid. So if we look at a structure here, so if we look at this structure here, you could go through and you can calculate your formal charge. This is actually the same structure that we showed when we were calculating formal charges, and we know that there's a minus on that oxygen. Now these electrons are known as delocalized because they're not going to be tied just to one specific oxygen. There can be movement, and what we're going to do is we'll focus a ton in class about the rules for movement. But we can show one of these lone pairs coming in to make a double bond here, and then this double bond breaking and forming a lone pair on that other oxygen. This could give us a new resonance structure that would look like this, where now that oxygen on top carries a negative charge rather than the oxygen on the bottom right. Now, these are both depictions of your resonance contributors, but neither of these is actually a true representation of what our molecule looks like. And we'll get to that in a second. But resonance is going to be a way in which we're going to depict a bunch of different ways of showing the exact same molecule, with the only difference being where electrons are. And we're going to be moving our delocalized electrons around throughout our molecule. So what are some of our core rules for our resonance? The very first and one of the most important ones that students will mess up the most is we are only moving electrons. We cannot move nuclei. We're not moving carbons. We're not moving hydrogens. We are only moving electrons. And the most common examples of electrons that we're going to be moving are going to be ones that are in double bonds and ones that are non-bonding, which are going to be our lone pairs. So double bonds and lone pairs are going to be things that we're moving, and we cannot move our nuclei, our carbons and our hydrogens. Each of these are going to be just a snapshot of the same structure. So you can't add more electrons or remove electrons. You need the same overall charge, where if your net overall charge in one was minus, your net overall charge in the second one must be minus. We're ultimately going to go through and we're going to draw a bunch of these different structures, and we'll often consider the stability for the major contributor. In general, there's going to be a handful of different kind of like considerations we're going to do. The first and most important is going to be full octets. If you can get a full octet, that structure is going to be a lot more stable than one that doesn't have a full octet. And when you think of like a carbocation, a carbon with a positive charge, that's going to be a structure that does not have a full octet. So generally, we're going to try to move that positive charge off of that carbon and onto something else, like a nitrogen or an oxygen. If everything does have a full octet, your major contributors are going to be the things that want that charge the most. And that's going to deal with electronegativity, where you want to put the, if you have a negative charge, you want to move that negative charge to the most electronegative element. Now, in general, the more resonance structures you have, the more you can delocalize or spread that electron out, will help increase your stability. Now, before we even start drawing a bunch of structures and stuff of that sort, I do kind of have, and I really like this analogy. I stole this from a textbook about resonance contributors. So we're going to be drawing a bunch of these different structures that have the same connectivity. The only thing that's different is going to be the amount of electrons, like not the amount, but where those electrons are, I should say. However, all of these different images we're going to draw are kind of just like figments of our imagination. They don't actually physically exist in the same sense that you might think. So to kind of provide an analogy, if I asked you to describe what a rhinoceros looks like, you might say, hey, it's a cross between a unicorn and a dragon. That's something that, can help people kind of figure it out, what it might look like. I think unicorn, okay, a horn. I can kind of see how that kind of gets me to like a rhinoceros. But much like unicorns and dragons, these resonance contributors don't actually exist. A rhinoceros doesn't like convert where 1 minute it looks like a unicorn and the next minute it looks like a dragon, in the same way that our molecules aren't just magically going to be like switching between. These electrons are going to be delocalized and everything's going to be always as that rhinoceros. The unicorn and the dragon are just kind of our depictions to kind of like help describe what that rhino looks like. If we actually think of like this structure up here, where we have these carbon single bonds and carbon double bonds to oxygens, a carbon oxygen single bond and a carbon oxygen double bond actually have different lengths. So a carbon oxygen single bond has a length of 1.36 angstroms, where a carbon oxygen double bond has a length of 1.2 angstroms. So it's held up a little bit tighter together. If you look at our structures like for above, you're not having that bond between your carbon and oxygen grow and shrink and grow and shrink and grow and shrink. It actually has a single length that is seen, and it's in between that of a double bond and a single bond, and it's at 1.26 angstroms. So these kind of depictions where we have here, like the image to the left and the image to the right, are kind of like these extrema that are kind of just depicting where those electrons are moving, but your molecule is actually not kind of like constantly like actively changing. The better depiction, and sometimes you'll actually see it, is if you draw something, well, maybe just over here. We have an R, a carbon, an oxygen, and an oxygen. And then here, each of these has 2 lone pairs. And then sometimes you'll see like a dotted line drawn here to say that there are electrons that are freely moving between this oxygen, this carbon, and this oxygen. And that's kind of a nicer way. Now, drawing these, especially when you have a lot of delocalization, can be really, really hard because you'll have a lot of dotted lines. So that's why we will draw these individual resonance structures. It's also super helpful to think about reactivity and stability and things. So there's a lot of merit to them, but I don't want you to kind of be confused to think like we're randomly switching between these. Realistically, these are kind of like our best depiction of a bunch of different structures that all exist kind of at the same time. And we're going to get a ton of practice in kind of like drawing a bunch of these. This is also why, if you remember at the end of last class when we were talking about that example where I said one of these looks like it's sp3, but it's actually sp2, it's because of resonance. So resonance can also mess with your hybridization a little bit, which we'll talk a ton about in class. Resonance can only happen between sp2 and sp orbitals. It cannot happen with sp3. sp3s are no-goes. So there's at least a little bit of background on resonance, and then we'll get a ton of practice on drawing what are our major types in terms of movements of positive and negative charges and what those each look like in class. So we'll go and end up there.